Digital data are available from a number of sources and provide a means for rapidly and inexpensively populating a GIS database. Most of these data have been produced by government organizations and are available at little or no cost, often via the internet. Data for elevation, transportation, water resources, soils, population, land cover, and imagery are available and should be evaluated when creating and using a GIS. Three important questions to ask about external data sets are the extent. Does it cover my area? The grain. Does it have an appropriate spatial resolution and accuracy? And attributes. Does it have what I need at an appropriate level of detail and consistency? Digital data are developed by governments because these data help provide basic public services such as safety, health, transportation, water, and energy. Because these data are often distributed at no cost, these existing digital data are often the easiest, quickest, and least expensive source for much spatial data. Data are increasingly collected in digital formats. GNSS, laser measurements, and satellite scanners all provide primary data in digital forms. They are directly transferable to GIS systems where they may be further processed. Digital collection eliminates data transfer from viewable physical media such as maps or written lists, and then converting these media into a digital form. A web service is a standard way of serving geographic data over the internet. GIS software accesses data via an internet connection, displaying these data on a local machine, although they are served from remote computing systems. Image data are most often served, but vector data may be also provided. The data don't reside on the local hard disk, and data are delivered in response to each pan, zoom, or other change in display. In contrast to a web service, we will primarily focus on data available for download, as these have the fewest barriers for use in analysis. But we'll discuss web services on this slide for completeness. A WMS is for serving cartographic data to produce and display maps, while WFS for vectors and WCS, primarily for rasters, deliver data and metadata in ways that ease spatial processing and analysis. Most data through services are currently provided as WMS, with few systems supporting and using the editing and analysis functions available through WFS and WCS. Web services have both advantages and disadvantages when compared to data stored on a local hard disk. Web services save space on the local hard drive, and only the portion of interest from a large data set need be accessed. Additionally, a community of users may share the data, for example, widely used government data, and then the most up-to-date information can be provided to a wide set of users. Many different kinds of data may be joined together more easily, as accessing web services typically only requires a few mouse clicks. On the downside, you may often not manipulate or change WMS data in any substantial way, and some kinds of analysis may not be supported or allowed. In these cases, local copies of the data are typically required. Furthermore, map services may also require a fast and reliable internet connection particularly for high-resolution image data or other large raster data sets. National digital data often may be obtained from a central source via the Internet. For example, Geosciences Australia provides a suite of data layers that may be accessed through the website or may be requested in hard copy form. Similar resources are available for Canada, most European countries, and many Asian and Latin American countries. A partial list of available data resources is included in Appendix B of our textbook. Global data are scarce because few governments collect spatial data in the same way or with the same set of attributes. Different governments specify different datums, standard map projections, data variables and attributes, or have different requirements for survey accuracy or measurement units. University centers or ad hoc collaborations are one source of global data. Here is an example from the collection of natural Earth data sets. This is a volunteer collaboration for creating consistent, high-quality data suitable for small-scale mapping. Given the substantial difficulties in compiling data from disparate government sources, the Global Spatial Dataset Infrastructure, or GSDI, initiative was formed. GSDI is an attempt to coordinate collection and processing methods worldwide to ensure that spatial data are broadly suitable for global-level analysis. A DEM stands for Digital Elevation Model, and it's a raster set of elevations, usually spaced in a uniform horizontal grid. Relatively high-resolution global digital elevation models are available from three sources. The oldest is the Shuttle Radar Topology Mission, SRTM, with data released at various resolutions worldwide. SRTM elevations are based on radar measurements from a NASA space shuttle in February 2000. The second widespread global elevation dataset is based on the Aster satellite and uses image stereo pairs collected in the early to mid-2000s. The third source of global DEM data comes from a pair of satellites launched and operated by the German Aerospace Center and the European Aeronautic Defense and Space Company. The satellite pairs are Terrasaurus and Tandemix, are based on combined radar signals in a tandem formation to measure elevation. The United States has defined the National Spatial Data Infrastructure, or NSDI, for the policies, technologies, and personnel required to ensure the efficient sharing and use of spatial data. The NSDI has developed a framework that identifies core data sets commonly used by many organizations. Framework data are created and maintained by a diverse set of organizations, both within and outside of governments. Framework data may reside anywhere, but will be submitted to the National Geospatial Data Clearinghouse, NGDC, for certification. Digital data are available for most of the United States through the National Map Project, described as a cornerstone of U.S. mapping efforts. Data are provided on political and civil boundaries, transportation, hydrography, geographic names, man-made structures, for example, dams, notable buildings, towers or monuments, elevations, aerial photographs, and land cover. Besides hydrography, the national map also distributes transportation, man-made structures, and boundaries data in vector formats. Transportation data represent roads, railroads, airports, and other transportation features. National map boundaries data identify national, state, county, and Native American lands, as well as the boundaries for cities and towns. Structures data identify selected man-made features, including government centers or service buildings, hospitals, and other important buildings, as well as dams, bridges, and key physical structures. Limited attribute data are provided with all of the national map vector data. Digital elevation models, DEMS, provide elevation data in a raster format and are available at 10-meter or better resolution for all states except Alaska, and are used commonly in data analysis and display. DEMS with 3, 10, and 30-meter horizontal sampling frequencies are available for much of the United States. Currently, the USGS delivers these DEMS as part of the National Elevation Dataset, or NED, through their portal, which is seen here on the slide. Data are available at 30-meter resolution for almost all of the United States and 10-meter resolution for the lower 48 states and Hawaii, and 3 meters for a large and expanding area of the continental United States. The National Hydrological Dataset, NHD, contains digital spatial data about surface waters, including rivers, streams, canals, ditches, lakes, ponds, springs, and wells. The NHD combines data from USGS digital line graph data and United States Environmental Protection Agency EPA river reach data. A reach is a segment of a stream, river, or coastline considered homogeneous under an EPA classification scheme. Naturally occurring and man-made features are represented in NHD data. These include water bodies, canals, pipelines, dams, and other natural or control structures. Attributes may be provided for these features, for example, a lake type or name, if a dam is earthen or concrete, or the type of ditch. Features may be points, lines, or polygons. NHD data are organized by areas in a hierarchically nested set of hydrological units identified by unique codes known as HUCs. NHD is a program to generate consistent, high-quality hydrographic data with elevation-based catchments. High-resolution digital image data are typically collected every 5 to 10 years by the USGS in partnerships with states and other government agencies. The high-resolution orthophotographs, HROs, are among the highest resolution widely available image data sets. The HRO images are collected and distributed through the USGS. Orthophotographs are created by using projection geometry and measurements to remove tilt, terrain, and perspective distortion from aerial photographs. Because they are orthophotographs, Object base locations have been corrected for tilt and terrain distortion at ground height. Towers, buildings, bridges, and other tall objects often appear to tilt as these structure heights are above ground are not corrected on the images. NAPE is primarily for one purpose, to monitor agricultural landscapes. NAPE photographs are typically acquired during the full leaf period for local crops, so the bulk of the images are collected from June through August. Images are most often derived from natural color photographs. NAPE images are most useful as a base for digitizing, particularly when information on vegetation type or condition is important. While land cover is important when managing many spatially distributed resources, data on land cover are quite expensive to obtain over large areas. These data are often scarce, at low categorical or spatial resolution, and rarely available over broad areas. The NLCD versions are produced in a cooperative effort by a number of U.S. federal government agencies under the Multi-Resolution Land Characteristics Consortium, MRLC. So these are sometimes referred to as MRLC data. The consortium's goal is a consistent current land cover data record for the conterminous United States. Here we see land cover maps that focus on distinguishing major crop types and rotations. These data are created from a combination of existing land cover data. Observed crop types are compared to spectral data from satellites and a classification algorithm developed. CDL data is produced annually for most regions, allowing analysis of trends in planting, crop rotations, and harvest. Data may be downloaded for regional, statewide, or sub-state areas in standard formats and standard coordinate systems. NWI data are produced by the United States Fish and Wildlife Service. NWI data portray the extent and characteristics of wetlands, including open water, and are available for approximately 90% of the conterminous United States. About 60% of the conterminous United States is available in digital formats. NWI, or National Wetlands Inventory data, were produced through a combination of field visits and air photo interpretation. Wetlands are categorized as a part of a lacustrine, palustrine, or riverine system. Lacustrine means lake, palustrine means pond. Subsystem designators then further specify attributes to record if the wetland is perennial, intermittent, littoral, or deep water. Littoral regions are regions along a shoreline. Statutory wetland definition typically includes not only surface water, but also characteristic vegetation or evidence on the surface or in the soils that indicates a period of saturation. The National Resource Conservation Service, NRCS, of the United States Department of Agriculture has developed 3 digital soil data sets. These data sets differ in the scale of the source maps or data, and thus in the spatial detail and extent of coverage. Data are most often digitized in a local zone UTM coordinate system and converted to a common Alpers equal area projection. Floods cause between 5 billion and 18 billion a year in damages, and this damage could be reduced with the effective application of GIS. A first step in reducing damage is the mapping of flood-prone areas. The Federal Emergency Management Agency, FEMA, develops and disseminates flood hazard maps, commonly known as floodplain maps. These maps locate the boundary areas with a 1% or higher annual chance of flooding, commonly known as 100-year floodplain maps. Floodplain maps are used for a number of purposes, chief among them setting flood insurance rates. Over 19,000 communities participate in the National Flood Insurance Program. The National Climatic Data Center, NCDC, maintains historical climate records for the United States and provides their data through their web portal. Recording stations may be selected by various criteria, including geography, measured variables, or length of record. Climate data have been converted to spatial fields and are distributed through the PRISM initiative by Oregon State University. Mineral resources data are available from the United States Geological Survey. These data include maps of basic national geology, as well as spatial and tabular data on specialized themes, such as mineral deposits, mines, claims, smelters, and other processing facilities and energy resources. The Tiger system is used to organize areas by state, county, census tract, and other units for data collection and reporting. It also allows the assignment of individual addresses to geographic entities. The Census Tiger system links geographic entities to census statistical data on population size, age, income, health, and other factors. The Tiger system is a key government tool in the collection of census data. Polygon features provided include census tabulation areas such as census block groups and tracts, and area landmarks such as parks and cemeteries. Point landmarks such as schools and churches may also be represented. Points, lines, and polygons are used to define these features. Many United States government datasets are provided with codes compatible with the United States Census Bureau data. And that concludes our lecture on data sources.